Hey everybody, Avery the Applications Astronaut here talking to you about related rates. Now I got a question for you students out there. What's an astronaut's favorite part of the computer? That's going to be the space bar.
First thing we're going to talk about are related rates. Those will be the rate of change of two or more related variables that are changing with respect to time. So there are a lot of different examples that we're going to do today. One such example would be down here. We have an upside down cone that is filled with some sort of liquid, let's say water. If water is continually poured into this cone or it's leaking out, the rate at which the height of this water is changing is directly related to the rate at which the volume of the water is changing. And because of that, we can actually set up an equation relating those rates, and that's where related rates come from. It's just an equation that relates two or more rates. Now, again, this is just one such example. There's going to be a bunch of different types of examples we're going to do today. Next thing we're going to talk about is how to solve a related rates problem. So the first thing I want you to know is that no two problems are the same. So these are going to be word problems, and they're going to ask you to find certain rates of change. But know that if you follow these guidelines, you'll get what you're looking for. So the very first thing you're going to do is you're going to make a sketch. You have to make a sketch. It's the most crucial part. When you make your sketch, you need to label all constant measures and give a variable to all changing measures. So when I say constant measures, what am I talking about? I'm talking about the length of a ladder, the height of a person. These things are not changing. They are constant measures. So you can label those with numbers. But a variable is going to be given to all changing measures. That would be like a person walking away from a lamppost. The distance they are from the lamppost is changing, so that needs a variable. It would be like if a ladder was leaning against a wall and then starts sliding down. The height that the ladder is up a wall will then need a variable because that's changing since the ladder is sliding down. So again, all constant measures you can just label with a number, the exact number that they are. But if a measure is changing, it must have a variable. After you do that, you're going to write an equation relating the variables whose rates of change either are given or are to be determined. Your equation is more often than not going to be a trig ratio or the Pythagorean theorem or a geometric area formula or a geometric volume formula. These are typically what your equations are going to be. Because then in the next step, you're going to use the chain rule and implicitly differentiate both sides of the equation with respect to time. So in your equation, when you take the derivative with respect to time, you will create dv dt or dr dt. You will create a bunch of different rates, which are then related because it's an equation. So that's how you get related rates. After you implicitly differentiate, you will then substitute into the resulting equation all known values for the variables and their rates of change. So you go back to example 1 when you wrote down all your known quantities, and you will take those and then plug them in to the equation that you implicitly differentiated. You will then solve for the required rate of change, and that's super easy. You just figure out, am I solving for dv dt, dr dt, dx dt? You will then solve for that specific rate of change.
Shoot for the stars. It's example time.
In example 1, it says an airplane is flying at an altitude of 6 miles on a flight path that will take it directly over a radar tracking station. The distance s from the plane to the station is decreasing at a rate of 400 miles per hour when s is equal to 10 miles. What is the speed of the plane? So first step in a related rates problem is to make a sketch. And in this sketch, we are going to label all constant measures with a number and all changing measures with a variable. So we have a plane flying at a specific altitude directly over a radar tracking station. So it's going to look something like this. Notice, for this specific moment in time, the altitude of the plane is not going to change. Yeah, eventually it's going to land. But as it flies over the radar tracking station, that altitude is going to remain constant. It's a constant 6 miles. So we can label this altitude as 6 miles. Now the distance from the plane to the station, that would be this dashed line right here, that is going to constantly change as this plane flies over the station, right? That distance. Because of that, it needs a variable, and it gives you that variable in the problem. It says the distance s from the plane to the station, so that's s right here. Now this distance right here is also changing. So because this is changing, it needs a variable. We're going to call it x. You could have put any other variable in there that you wanted to. Now, one of the biggest mistakes that people make on these problems would be that they plug in numbers for measures that are changing too early. So this S is equal to 10 miles. You can't plug this in right away. Otherwise, when you take the derivative, it'll just disappear. So what we want to do is any measures that are changing, we want to leave them with a variable for right now. We will plug this in later on, I promise. So now, the other part of the first step is to state all given quantities and quantities to be determined. So we'll start with our given quantities. What are we given? We're given that the altitude is 6 miles, so we already put that on here. We're also given that the distance S from the plane to the station is decreasing at a rate of 400 miles per hour. So how do we write a rate? Well, that's going to be d something dt. In this case, it's the rate at which S is decreasing. So it's going to be ds dt, and it's decreasing at a rate of 400 miles per hour. So we're going to say ds dt is equal to negative 400 miles per hour. Now, what are we trying to find? What are our quantities to be determined? We are trying to figure out what is the speed of the plane. So how would we do that with this particular figure? Well, the speed of the plane is the rate at which it travels horizontally, which would be the rate at which x is changing. So that would be dx dt. And we're trying to find this at a particular moment. We're trying to find the speed of the plane when s is equal to 10 miles. Now that we know what we're given and what we're trying to find, we can move on to step 2, which is to write our equation. Now remember, your equation is going to be something like the Pythagorean theorem, similar triangles, trig ratios, geometric volume formulas. That's what you're going to use for your equation. Now, in this particular figure, you can see that we have a right triangle that we have created, and we have 3 sides of a right triangle. So what equation relates 3 sides of a right triangle? Well, that's the Pythagorean theorem, right? We know that a squared plus b squared equals c squared. So that's what we're going to do. We're going to go x squared plus 6 squared is equal to s squared. Now that we have our equation, we can move on to step 3, which is to implicitly differentiate both sides with respect to time. So we're going to take our equation here, and we're going to take the derivative of this with respect to time. Now notice, none of these variables are t, which means we're going to take the derivative, but then we're going to have to tack on a dx dt or a ds dt. So here's how this works. We're going to take the derivative of both sides with respect to time. Derivative over here, this is going to become 2x to the first. But since we're taking the derivative with respect to time, that's not the same variable as x. So we're going to tack on a dx dt. Derivative of 6 squared, that's just 36. So the derivative of 36 is going to be 0, because when you take the derivative of a constant, you just get 0. Over here, when you take the derivative of s squared, you get 2s to the first power. But since you're taking the derivative with respect to time, this is an s, that's not t, so we tack on a ds dt. Now we simplify this, 2x dx dt plus 0 is just 2x dx dt. Now this equation is relating to rates, dx dt and ds dt. That's why it's a related rates problem. Now we can move on to step 4, which is to substitute all known quantities. So we know that 2x dx dt is equal to 2s ds dt. We also know that ds dt is equal to negative 400 miles per hour. So we can take negative 400 and plug it in for ds dt. Now we're also trying to figure out what dx dt equals when s is equal to 10. So after we differentiate, now we can take that 10 and plug it in for s here. That's why we have 2 times 10 times negative 400 over here. So there are 2 things we don't know. We don't know dx dt, which is what we're trying to find, so that's what we're going to end up solving for. We also don't know what x is. So is there a way we can figure out x at this particular moment in time? Well, if we look at our figure, at this specific moment, this side is equal to 6 and s has to equal 10. So we can actually create a Pythagorean theorem equation where it's x squared plus 6 squared is equal to 10 squared. And that'll tell us what x is at this given moment. So here I square the 6, I square the 10, and now I subtract 36 on both sides, square root both sides, I get x is equal to 8. So at this moment in time, s is equal to 10, the altitude is 6 miles, and x has to equal 8. So I'm going to plug in 8 for x here. Now all I have to do is solve for the rate that I'm looking for. So I'm going to solve for dx dt by simplifying both sides, then dividing both sides by 16, and I get dx dt is equal to negative 500 miles per hour. Now we look, what was the question asking? It's asking what is the speed of the plane? Remember, speed is the absolute value of velocity. So we found that the velocity of the plane is negative 500 miles per hour because it's going to the left 500 miles per hour. So the speed of the plane would be the absolute value of that. So the speed of the plane when s is equal to 10 miles is positive 500 miles per hour. Now, example 2 says a boat is being pulled into a dock by a rope attached to it and passing through a pulley on the dock position 5 meters higher than the boat. If the rope is being pulled in at a rate of 4 meters per second, what rate is the angle between the rope and the dock changing when the boat is 12 meters away from the dock? So first step in a related rates problem is to make a sketch. So how does this look? Well, we have a dock that is 5 meters high. It then has a pulley on top that has a rope going through it that's connected to a boat that's out here in the water somewhere. So we're going to say it looks something like this. We got our dock, we got the pulley, we got the rope, and we got our boat. Now, we're going to label all constant measures, and we're just going to put the number in there. So is there anything that's not changing? Well, the height of the dock is not going to change, right? It's always going to be 5 meters higher than the boat. So we could say that this dock is always going to be 5 meters high. Anything else that's changing has to have a variable. So there's a couple things in here that are changing. The length of the rope is obviously changing, right? As this boat is being pulled in, the length of this rope is changing. So we're going to call that length S. This length right here, this distance between the boat and the dock, that's changing because the boat is being pulled in. So we're going to give that a variable. We'll call it X. Doesn't matter. You could pick any other variable. We also know from our problem, what we're trying to find is the rate at which the angle between the rope and the dock is changing. So this angle right here is changing, and we're trying to find the rate at which that's changing. So we're going to say that this angle right here is theta, because that's the variable that we usually put for angles. Sweet. So we have drawn our figure, we've labeled it. Now we can state all given quantities. So what are we given? Again, we're given the height of the dock is 5 meters, and we're given that the rope is being pulled in at a rate of 4 meters per second. So how would we write that? Well, if the rope is being pulled in at a rate of 4 meters per second, S is decreasing. So that would be negative. So the rate at which S is changing, the rate at which S is decreasing, ds dt, is going to be negative 4 meters per second. So that's going to be it for our given quantities. We now need to figure out what are our quantities to be determined. What are we trying to find? Well, it says, at what rate is the angle between the rope and the dock changing when the boat is 12 meters away from the dock? So we're trying to find the rate at which this angle is changing. So d theta dt. When the boat is 12 meters away from the dock. So when x is equal to 12. Again, one of the biggest mistakes that people make in related rates problems is they plug in values like this to our figure too early. This 12, we need to plug in at the end. We can't plug this in right away, otherwise it'll mess up our equation. So that brings us to step 2, which is our equation. And remember, our equation is going to be the Pythagorean theorem. It's going to be similar triangles. It's going to be trig ratios. It's going to be geometric volume formulas. One of those things is what we're going to plug in for our equation here. Based on our figure, what equation can we make? Well, we are trying to figure out what d theta dt is, meaning that theta obviously needs to be part of our equation. We also have the makings of a right triangle here, meaning that we could probably figure out a trig ratio that involves theta and then 2 of these sides. Well, in our given quantities, we know ds dt is negative 4 meters per second. So we want s in our equation because when we take the derivative, then we can plug in something for ds dt. It seems like we would want x in our equation also because of this, but there is no information about dx dt, the rate at which the boat is coming in. So we don't want to put x in our equation actually. What we do want to put is our constant measure over here, 5 meters. So I'm going to relate this angle, the adjacent side, and the hypotenuse of our right triangle here. How do we relate those? What trig ratio deals with adjacent and hypotenuse? That would be cosine. So we're going to say cosine of this angle is equal to the adjacent side over the hypotenuse. Now, we move on to step 3, which is to implicitly differentiate both sides of this equation with respect to time. Now, this looks like it'd be really hard to implicitly differentiate, but it's actually not too bad. When you take the derivative of cosine of theta with respect to time, you just take the derivative of cosine, which is going to be negative sine. So you write negative sine of theta times d theta dt because you're differentiating with respect to time, not theta. Over on this side, remember, 5 over s is the exact same as 5 times s to the negative first power. So when I take the derivative of this, the 5 stays out front. The s to the negative first, I take that negative 1, move it to the front, and becomes negative 1 s to the negative second power. So then that becomes negative 5 s to the negative second, or negative 5 over s squared. And since I'm taking the derivative with respect to time, I have to multiply by ds dt. That's where this comes from. Now, I have an equation that relates to rates. That's why this is a related rates problem. So we can move on to step 4, which is to substitute all known values. So in this equation down here, I know at this particular moment in time, ds dt is equal to -4 meters per second. So I'm going to take -4, plug it in for ds dt. Now, it does seem like I should be able to plug in something else, but I don't have s at this particular moment in time. What I do have is a right triangle, and I know this side has to be 5, and I know at this moment, x has to equal 12. Well, if I know this side of the right triangle is 5 and this side has to be 12, then couldn't I figure out what s is? Yeah, I could just use the Pythagorean theorem. So at this particular moment in time, if this side of the right triangle is 5 and this side is 12, then what I do is 5 squared plus 12 squared is equal to s squared. I then simplify that and I get s squared is equal to 169, square root both sides, I get s is equal to 13. So at this moment, s has to equal 13. So I can plug in 13 for s. Sweet. Now, I need to solve for d theta dt. That's the whole point of this problem. So what am I going to do with this negative sine theta? Well, I can take this and divide it to the other side. And when you divide by negative sine theta, it's the same as multiplying by the reciprocal, which would be negative cosecant theta over here. Now, how does that help us? Well, at this particular moment in time, we figured out this right triangle. This is 5, this is 12, and this is 13. So cosecant, if you recall, is hypotenuse over opposite side. So from this angle, the hypotenuse would be 13, the opposite side would be this 12. So cosecant of theta at this particular moment, we can rewrite as 13 over 12. And then we just tack on that negative that was out front. Then we simplify this over here, multiply these two fractions together, and in our calculator we get that d theta dt, the rate at which this angle is changing with respect to time, is negative 0.128 radians per second. Now again, it's a word problem, so you need to answer in a sentence. It says, what rate is the angle between the rope and the dock changing when the boat is 12 meters away from the dock? The rate at which that angle is changing is approximately negative 0.128 radians per second. Now example 3 says a conical cup is 4 centimeters across and 6 centimeters deep. Water leaks out of the bottom at a rate of 2 cubic centimeters per second. How fast is the water level dropping when the height of the water is 3 centimeters? So the very first thing we're going to do is we're going to make a sketch. So here we have a conical cup that has water in it. So it's going to look something like this. We have our conical cup and we have the water in the cup. Next, we're going to label this with any constant measures. So with any constant measures, we're going to put a number. So our conical cup, would the radius of that cup ever be changing? No. Would the height of that cup be changing? No. So we can put that since the conical cup is 4 centimeters across, we know that the radius has to be 2 centimeters. And since it's 6 centimeters deep, we know that the height of our conical cup has to be 6 centimeters. Those things are not changing. That's why we can label our sketch with numbers for those specific measurements. Now, what is changing? Well, we know that water is leaking out of the bottom of the cup. So wouldn't the water be changing? Wouldn't the radius of the water as the water leaked out, wouldn't that be getting smaller? And wouldn't the height also be getting smaller as the water leaked out? Yeah, so those two measurements then would be changing, meaning that they need variables. So the radius of the water, we're just going to call R, and then the height of the water, we can just call H. Now that we've made our sketch and correctly labeled it, we can move on to the next part of step 1, which is to state our given quantities. Now, what are we given here? Well, again, we're given that we have a conical cup that's 4 centimeters across and 6 centimeters deep. So since it's 4 centimeters across, we know the radius is 2 centimeters and the height, since it's 6 centimeters deep, is 6 centimeters. We also know that water leaks out of the bottom at a rate of 2 cubic centimeters per second. Now, notice the units here. Cubic centimeters refers to volume. So since it's cubic centimeters per second, that would be the rate at which the volume of this water right here is changing. So it's changing at a rate of negative 2 cubic centimeters per second because it's draining out of the bottom of the cup. Next, what are we trying to find? What are our quantities to be determined? Well, it says how fast is the water level dropping when the height of the water is 3 centimeters. So how fast is the water level dropping? That would be the rate at which the water level is dropping, meaning the rate at which the height of the water is changing. So we're trying to find dH dt, the rate at which the height of the water is changing when H is equal to 3 centimeters. Now again, one of the most commonly made mistakes is taking this 3 centimeters and plugging it in for H right away. what happens is h is something that is changing. So we need to have a variable in here for it when we take the derivative. That way we get a dh dt. That way we have what we want to solve for. So let's move on to step 2, which is to write our equation that we're going to take the derivative of implicitly. So remember, our equation is going to be like Pythagorean theorem. It's going to be similar triangles. It's going to be trig identities. It's going to be geometric volume formulas. It's going to be something like that. So in this particular example, we see that we have dv dt given to us, which is the derivative of the volume, which means that our equation should probably involve volume. Well, what are we finding the volume of? Well, it's a conical cup, so wouldn't it be a cone? Now, what's the volume of a cone formula? Well, that would be 1/3 pi r squared h. So that is going to be our equation that we're going to take the derivative of implicitly with respect to time. Now, there is one issue here. We have an r squared and an h that are our independent variables. Now, in the past 2 problems, we've only had one independent variable, and that needs to happen. You can only have one independent variable. Otherwise, when you take the derivative, you're going to have to use the product rule, and it's going to get really messy with a dr dt and a dh dt. So we don't want to do that. We just want one independent variable. So how do we do this? Well, in our figure over here, we actually have 2 similar cones. We have this big cone, that's the cup, and we have the cone formed by the water. So what we can do then is set up a proportion that relates the radius and height of the cup to the radius and height of the cone. We can say that 2/6 is equal to r over h. Now what we can do is solve this for either r or h and plug that in to this volume formula over here, and we'll only have one independent variable. So do we want to solve for r or h? Well, let's look at what the question is asking us. We are trying to find dh dt, meaning that when we take the derivative, we want to make sure that there's an h in the formula, meaning we want to get rid of r. So we're going to solve this for r. We cross multiply and we divide both sides by 6 and we simplify and we get r is actually equal to h over 3. Now, how does that help us? Well, we can take h over 3 and plug it in this volume formula for r. Now what we can do is square this, so we can square the h and the 3, and then we can multiply it to this h that's out here. That's how we get h cubed over 9. We can then bring this pi up to the numerator, multiply the 9 and the 3 together, and we end up getting 27 in our denominator. We can then take the derivative of this. Now, remember, pi over 27, that's just a constant that we can move out front. So when we take the derivative of this, we're just taking the derivative of h cubed. So that's going to be 3h squared dh dt. Now, the 3 we multiply to the pi over 27, and the 3 and the 27 just cancel each other out. That's how we get pi h squared over 9 times dh dt. Now, we have an equation that relates 2 rates. That's why this is a related rates question. We can then move on to step 4, which is to substitute all known quantities. So what do we know here? Well, we know that dv dt is equal to -2 cubic centimeters per second. So we plug in -2 here. We know that we're trying to find dh dt, so that's just going to stay dh dt. And we're trying to find it when h is equal to 3. So we can actually now take that 3 and plug it in for h here. Sweet, we've substituted it in. Now all we have to do is solve for dh dt, the rate at which the height is changing. So to solve this, we just square the 3, that becomes 9. It cancels out with the 9 in the denominator. We then divide both sides by pi, and we get dh dt is equal to -2 over pi. Or if we want to round it to the nearest thousandth, we just put that in our calculator and we write dh dt is approximately equal to -0.637 centimeters per second. Now, this is a word problem, so we need to answer in a sentence. We say that the water level is dropping at a rate of -0.637 centimeters per second when the height of the water is 3 centimeters. Now, example 4 says a rocket's position function, s equals 50t squared, models the height of the rocket in feet, s, after a given number of seconds, t. If a camera is recording the launch at ground level from 2,000 feet away, find the rate of change in the angle of elevation of the camera at 10 seconds after liftoff. So the very first thing we're going to do is step 1, make a sketch. So we're going to make a sketch of what this looks like. We have a rocket that is taking off, and we have a certain distance away, 2,000 feet away, we have a camera that is at ground level that is watching the rocket take off. So for me, it's going to look something like this. We have our rocket taking off, we have a certain distance away, the camera at ground level that is watching the rocket take off. Now what we have to do is label all measures that are constant with a number, and then any measure that's changing, we have to label with a variable. So is there anything that's constant, any measure here that's not changing? Yeah, this camera is always going to be 2,000 feet away from the launch pad. So we can say that this distance right here has to be 2,000 feet. The camera is not moving back or forward. Is there anything else that is constant? No, but there are a lot of measures that are changing, which means we have a lot of variables to add here. So this rocket is taking off. This distance the rocket is from the ground is changing. Because of that, it needs a variable. So what variable? Well, normally you could just pick, but in the problem, it actually tells you what the height of the rocket is. That's S. So we're going to label this height S. We also know that the angle of elevation created by the ground and the line of sight of the camera to the rocket is also changing. So we're going to label this with a variable. And again, usually when we create a variable for an angle, we call it theta. Anything else? Yeah, the distance, I guess, from the camera to the rocket is also changing. So we can label that with another variable. You can pick this time. It's just R. Now, after we've labeled our figure, giving all constant measures a number and all changing measures a variable, we can move on to the next part of step one, which is to state all given quantities. So what are we given here? Well, we're given that the camera is 2,000 feet away from the launch pad, and we're given the position function for the rocket. It's S equals 50t squared. But I think that's it. So what are we trying to find then? What are quantities to be determined? Well, it says we want to find the rate of change of the angle of elevation of the camera 10 seconds after liftoff. So we're trying to find the rate of change of the angle of elevation, meaning we want the rate of change of this variable right here. So d theta dt at 10 seconds after liftoff. So when t equals 10. Now that we've found our given quantities and quantities to be determined, we can move on to step two, which is to write our equation. And again, our equation is typically going to be Pythagorean theorem, similar triangles, trig ratios, or geometric volume formulas, something like that. In this instance, we are trying to find d theta dt. Because of that, we want to make sure that theta is involved in our equation. So how can we create an equation here based on what we're given that involves theta? Well, we do have a right triangle, and since we want theta included, let's make a trig ratio. We just need two sides. We don't need all three. So I'm going to leave out r. There was nothing in the problem about r. We do have some stuff about s, and 2,000, it's always nice to have a constant in your trig ratio. It makes it a little easier. So what I'm going to do is relate this side and this side. So how is theta related to opposite and adjacent? Well, that would be tan, right? So we go tan of theta, tangent of theta is equal to s over 2,000. Now that we have our equation, we can just take the derivative of it implicitly with respect to time. So how do we take the derivative of this implicitly with respect to time? Well, if you recall, we're taking the derivative with respect to time, meaning that when you take the derivative of tan of theta, we're going to use the chain rule and take the derivative of tan first, which is just secant squared. So we're going to write secant squared theta. But since we're taking the derivative with respect to time, we have to tack on a d theta dt. So it's going to be secant squared theta d theta dt. Over here, s over 2,000. That looks complicated, but you can actually rewrite this as 1 over 2,000 times s, because technically 1 over 2,000 is just a constant that you can move out front. And then you're just taking the derivative of s with respect to time. So what's the derivative of s with respect to time? Well, derivative of a variable is just 1, but since we're taking it with respect to time, t, we have to tack on a ds dt. So that's how that looks. Now, I have an equation that relates to rates. That's why this is a related rates problem. So once we have this, we can then move on to step 4, which is to substitute all known values. So we look, oh, we're not really given anything besides this 2,000 feet from the launch pad, and that's already in our problem. So there's nothing I can really substitute yet. But I need to get rid of this ds dt and this secant squared theta. So let's start with this ds dt. How can we get rid of this? Well, we're trying to find d theta dt when t is equal to 10 at this particular moment in time. Well, I do have a position function for the rocket, s is equal to 50t squared. If I took the derivative of this with respect to time, wouldn't I get ds dt? And then couldn't I then plug in 10 for t and solve for ds dt? Yeah, let's do that. So we're going to take this position function, s is equal to 50t squared. We're going to take the derivative of it with respect to time, t. So when you take the derivative of s with respect to time, you get ds dt. When you take the derivative over here, the 50 stays out front by the constant multiple rule. You just take the derivative of t squared, which is 2t to the first. Then you multiply the 2 to the 50 and you get 100t to the first. That's ds dt. Now we want dsdt at a specific moment in time when t is equal to 10. So we're going to take 10, plug it in here, and we end up getting that dsdt at time t equals 10 seconds after liftoff, is going to be equal 1,000 feet per second. Now we can take that and plug it in for dsdt here. Sweet. Now we can move on to step 5, which involves solving for d theta dt. So all we have to do then is multiply these two together. 1,000 times 1 over 2,000, that just equals 1/2. And then we can divide both sides by secant squared theta. When you divide by secant squared theta, it's the same as multiplying by the reciprocal, which would be cosine squared theta. So it looks something like this. Oh, well, maybe I did this too early. I don't know what cosine squared theta is. Well, I do know that cosine squared theta is just the same thing as cosine of theta being squared. So we just need to figure out what cosine of theta is. Well, if we remember SOHCAHTOA correctly, cosine is equal to adjacent over hypotenuse. So I just need to figure out in this problem, what is cosine of theta? What is the adjacent side over the hypotenuse? And then I can plug that in here. Well, it's just 2,000 over r, but I don't know what r is. What is r? Well, at time t equals 10, couldn't we figure out what r is? Yeah, there's got to be a way to do that, right? We do have a right triangle here, so could I use the Pythagorean theorem again? I could go 2,000 squared plus s squared is equal to r squared. Yeah, let's do that. But then what is s at time t equals 10? Is there a way to find that out? Yeah, we do have a position function for s that tells us at any given time what s is equal to. So we're going to take s is equal to 50t squared, and we're going to plug in 10 for t. And when we do that, we get 5,000. That means s is equal to 5,000 at time t equals 10 seconds after liftoff. So we can then use the Pythagorean theorem to figure out what r is, our hypotenuse, at this given moment. So we go 2,000 squared plus 5,000 squared is equal to r squared. We then solve for r by taking the square root of both sides, and we get that r is equal to the square root of 2,000 squared plus 5,000 squared. So if we want to substitute in for cosine of theta, it's just equal to our adjacent side, 2,000, over our hypotenuse, which is the square root of 2,000 squared plus 5,000 squared. Now, remember, it's cosine squared theta. That's why this whole thing is being squared. We then just simplify this. Just plug this in your calculator, and you get that d theta dt is approximately equal to 0.069 radians per second. Again, this is a word problem, so you need to answer in a sentence. The rate of change and the angle of elevation of the camera at time t equals 10 seconds after liftoff, is approximately 0.069 radians per second.